Hello everyone. In this video, we're going to talk about high-performance computing and how it can benefit from heterogeneous integration. High-performance computing is the powerhouse behind large machine learning models, which are more generally known as artificial intelligence. And there's strong potential for advanced packaging techniques to provide lots of benefits for AI, like reduced manufacturing costs or increased efficiency and overall performance. The performance of AI systems is important because the global market for AI is expected to reach 407 billion USD by 2027, whereas last year in 2022 it was 86.9 billion. Since 2022, there have been lots of impactful updates to systems you've probably heard of or maybe even played around with, and there's likely more to come. Chatbots like ChatGPT or image generators like Stable Diffusion that have grown in popularity significantly can primarily attribute that development to the advances in algorithm programming that have made them so much smarter. And to continue this growth and support these new algorithms, the computing capability needs to follow. And these days, the cost of manufacturing a whole system on chip and making it as small as possible is far too expensive. Heterogeneous integration allows individual chips to be produced at cheaper costs with more design flexibility and scaling compatibility, using advanced packaging to connect them all together and run these AI algorithms. The applications of which are practically endless. It's being used in sensors of self-driving cars, the voice recognition on your phone for Siri or Shazam. Businesses are using it to process and organize large amounts of data, and lots of industries are starting to adopt AI technology from healthcare to cybersecurity, and of course the manufacturing industries. So it's important to find better ways to package the hardware that enables AI to solve these data-based problems, and specifically to support large machine learning models, which are systems that are very adept at analyzing a lot of unstructured data. These models with potentially hundreds of matrices with millions to billions of weight parameters between them are responsible for taking the input layer and transforming it through many iterations and calculations to the output layer. And the data between these iterations has to be stored in a memory unit and accessed by a processing unit multiple times over, meaning these large machine learning models need the ability to store and transport lots of data, which they achieve using high bandwidth memory. Now, machine learning is a requirement for AI systems to teach them about their environment so they have a base of knowledge to refer to. And a majority of the power consumed by these iterations is spent on matrix multiplication, so they benefit greatly from parallel computing. And new methods of enabling parallel computing, and more directly high-performance computing, are the key to improving the efficiency of these machine learning models, as the conventional methods of computing are providing diminishing returns. One of those methods is the CPU, or Central Processing Unit, that can tackle a wide range of the problems that you throw at it, but it can't do any one thing particularly well. On the other hand, the graphics processing unit, or GPU, is much better at specialized tasks, and the benefit is that it has a lot more cores that can run simultaneously, but the downside is that it consumes a lot more power compared to a CPU. Now, the GPU was initially designed to be good at 3D game rendering, so as a side effect, it's able to manage these huge batches of data, and the parallel computing style it works with is very advantageous for AI, because it can spread the workload amongst these multiple accelerators. Each individual accelerator or worker can take a subset of the data, determine its own changes to the model, and then exchange its weight changes and synchronize with the other workers. But of course, with this much talking between your accelerators, it's really important that you have high bandwidth communication and quality interconnects. And it's so important so that NVIDIA even developed their own GPU that was specifically designed to tackle the demands of AI computing. The three biggest demands being high bandwidth access to memory, efficient chip-to-chip connectivity, and a high compute density. Now the NVIDIA GPU that was mentioned in the previous slide is shown again here, and you can see that there are these high bandwidth memory stacks that are on the same physical package as the GPU's processing core, and this provides these power and area savings that allow more cores to be installed into systems. And the biggest three needs of high-performance computing are cared for, using this interposer for high bandwidth connection to the memory and other chips, and these 3D stacks of memory for high compute density. And as these AI models are becoming increasingly more complex, it'll be more important to find ways that make them more efficient. And the coupling of heterogeneous integration and advanced AI models can lead to these major advancements in performance and capability of what they can do. But specifically working to improve the interconnection quality between your logic and memory and reducing the energy cost per bit will be the primary ways to make high-performance computing more efficient. One of the ways this can be done is using an interposer, or a passive entity that enables connections between chips among a common packaging substrate. Now, the standard is the silicon interposer, which uses through-silicon vias and redistribution layers to form conductive pathways between chips. And this type of interposer has been covered before in the packaging series, so more specific information can be found there. But here, we want something that's easy to manufacture and that enables high bandwidth, but the use of dielectric silicon dioxide can cause a high capacitance between connection lines and limit the max signal data rate. Now, an alternative is the glass interposer, which uses a lower cost polymer or ceramic-based substrate that has a lower dielectric constant to mitigate this issue and yield a 5 to 10 times improvement in data transfer rates. The glass interposer provides a significant advantage compared to the silicon interposer, and it helps maximize the quality and efficiency of fine-pitch interconnects. Now, there are two issues with the conventional interposer, and that's when spacing is too small between interconnects, the capacitance between them is very high, and this is proven with the formula for capacitance. Now, when the cross-sectional area of the interconnecting wires themselves is very small, the resistance will become very high, and this is a simple relationship of resistance to geometry. And the combination of these two ends up limiting the max data rate that can be transferred through them. And if we consider a confined space to work with, if we increase the width of our interconnections to mitigate resistance, we end up decreasing the spacing between the lines, and thus we end up increasing the capacitance between them. Now, if we try to reduce the capacitance by increasing spacing, we effectively have to reduce the width of our lines, resulting in increased resistance. But by using a dielectric material for the interposer that has a permittivity lower than the conventional silicon dioxide, we have more freedom to modify the spacing and in turn the line width to maximize performance. Now, the glass interposer can enable both lower latency and reduced crosstalk with higher data transfer rates and by consuming lower energy. Beyond using interposers to just tile chips horizontally on the same substrate, we can also think about stacking them vertically on top of each other. We can use the same concepts of through-silicon vias and redistribution layers to form communication lines between vertically stacked dies in order to improve the bandwidth and efficiency between components. And this is done by decreasing the travel length of the communication lines, which effectively reduces the resistance. Now, if we wanted to go a step further, we could discover a viable material that has a lower resistivity, but in general, we can see significant improvements in bandwidth and energy per bit from using 3D integration methods compared to 2D. But as always, there are some downsides that arise when you actually put this into practice, depending on the way that you stack the memory and accelerator components. Now, if we stack the accelerator on top, it makes it difficult to push power through the memory layers and to the accelerator, but it makes it a lot easier to dissipate the heat generated by the accelerator. Now, if we stack the memory on top, that makes the power delivery aspect easy, but it makes it really difficult to dissipate the heat that's generated from the accelerator. Now, there are alternative methods though, like how NVIDIA constructed their GPU by making these 3D memory stacks placed next to an accelerator. But ultimately, the quality and efficiency of interfaces between your accelerators and memory or specialized components and the rest of the system really determines how beneficial 3D integration can be. Another way to achieve 3D stacking with better interconnections is by using optical connections, as they can improve the stackability and versatility compared to hardwired electrical connections. As you continue to stack chips higher and higher with hard wires, the failure rate dramatically starts to spike because you have to expose the system to high temperatures during post-processing of bonding layers together. But one of the ways that optical connections are being used currently is this duo combination of a photodiode and a light-emitting diode to receive the information from the layer below and transfer it to the layer above. Instead of dealing with electronic properties, we can take advantage of 3-5 based optical systems and use the speed of light to transfer information in a way that results in no crosstalk between the lines. The layers simply need to be aligned such that the LED of one layer lines up with the photodiode of the next, and you avoid the high processing temperatures that can destroy your yield rates. And effectively, you have individual layers that can have their own purposes, being processing, memory, or for specialized AI computing, that can communicate using light and are easier to reconfigure and stack. Computer architecture refers to the design and organization of hardware and software components, and it's the fundamental principles and structures that govern how the computer operates. And one of the ways in which high-performance computing is being developed is by switching AI-specific hardware away from the conventional von Neumann architecture, which is a type of stored program computer architecture where the data and instructions are stored in the same memory and accessed sequentially by the CPU. But with this architecture, the CPU has to fetch the instructions from the memory, decode them, execute them, and then store the results back in the memory. And while it allows for a high degree of flexibility and has been widely used in many computing devices, it suffers from bottleneck issues when you're trying to process large amounts of data because it can't take full advantage of high bandwidth area interfaces. Now, what's being developed is called the neuromorphic architecture, which is modeled after the structure and function of the human brain's neural networks. It mimics neurons and synapses by using analog and digital circuits and is especially skilled at parallel data processing. The neuromorphic architecture is capable of processing large amounts of data very quickly while consuming little power and can learn from experience and adapt to new situations, making it ideal for applications like image and speech recognition. Now, the emergence of neuromorphic architecture provides many new opportunities and challenges to packaging, and finding ways to integrate specialized hardware will be a key driver in AI development. A piece of specialized hardware that's disrupting the idea of separately packaging your processors and memory devices is the Memristor, or the memory resistor, which is a programmable resistor that can function as a processor and memory. This type of device is still an active area of research, being first demonstrated in 2008, and it's highly compatible with the neuromorphic computing architectures because it works like a synapse. The structure is a titanium dioxide thin film with length L that's sandwiched between platinum electrodes. Now, one side of the titanium dioxide crystal will have oxygen vacancies, and these are the absence of oxygen molecules in the lattice. But when a negative voltage is applied to one of the platinum electrodes, like the one on the left here, these oxygen vacancies will migrate away from the interface like they already have, making the interface material more like titanium dioxide with a wider band gap and a higher resistivity. Now, applying a positive voltage will have the opposite effect and decrease the resistivity as oxygen vacancies diffuse towards the interface. Now, this allows the Memristor to store information in the form of two distinct resistive states, being high and low, and it allows it to not always be deterministic. It knows the relative magnitude of voltage that was applied previously, and that can be used to consolidate processor and memory functions into the single component, and it can achieve an impressive integration density that's a few times higher than flash memory technologies. The biggest challenge lies in integrating memristors and specialized AI processors with existing IC fabrication and packaging techniques. And that's all I have for this video. I hope you learned something about AI and packaging and that you're excited for the future of this technology because there's lots of cool things being researched and developed that we'll be able to take advantage of in the coming years. Take care.